Oh, dear students, in the last two classes, we have seen organophosphates and synthetic pyrethroids. Today, we will see how these two groups of insecticides, organophosphates as well as synthetic pyrethroids, act on the insect system. So, what is the mode of action of organophosphates and carbamates? No answer? You can type it. You can type it. Acetylcholinesterase inhibitors. Yes. Acetylcholinesterase inhibitors. Yes, fine. So, all organophosphates and carbamates are acetylcholinesterase inhibitors, whereas synthetic pyrethroids are sodium channel blockers. Yes, yes, acts on sodium channel. So, today we will be seeing how uh, these insects acts on how typically the physiological level how these insecticides acts on these two sodium channels as well as acetylcholinesterase. Have you gone through the videos I have posted in the Moodle for both organophosphates and synthetic pyrethroids? Yes or no? I have given you some reading material. Yes, okay, fine. If you have gone through that video, if anyone has not viewed that videos, uh, view it again because that will be extremely helpful for you to understand the process of acetylcholinesterase inhibition as well as sodium channel blocking by organophosphates and synthetic pyrethroids respectively. So first, today's class I will be covering both. In the first half an hour, I will be discussing about acetylcholinesterase inhibition, and in the second half I will be discussing about sodium channel blocking. So coming to acetylcholinesterase inhibition, the basic things are known to you. I will ask questions and you can answer. Okay. How nerve impulse is transmitted across a synapse? So, what is the neurotransmitter in a synapse in insects as well as human beings? What is the neurotransmitter in the acetylcholine? Yes, good. So acetylcholine is the neurotransmitter. The acetylcholine, yes, the space between the presynaptic membrane and postsynaptic membrane is called as synaptic cleft. It is also called as synapse or synaptic cleft also. Okay. So the in the presynaptic membrane, the acetylcholine is enclosed in structures called as synaptic vesicles. I think if you remember that. So I will show the diagram of it, then I will explain it. Okay. So this is the presynaptic area. This is the postsynaptic membrane. This is the acetylcholine enclosed in synaptic vesicles. So when a signal reaches the here, the synaptic vesicles reaches over to the presynaptic membrane. This is the presynaptic membrane. This is the synapse, the gap between the presynaptic membrane and the postsynaptic membrane. The acetylcholine will be released into the synapse by the synaptic vesicle. So acetylcholine is released, and on the postsynaptic membrane, this is the postsynaptic membrane, we have receptors for acetylcholine. We call it as acetylcholine receptors. These are nothing but proteins. What you see, these receptors are nothing but proteins to which this acetylcholine binds. So what will happen once acetylcholine binds to the receptor? This is just like a key which is used to open a lock. The acetylcholine is a key and the receptor is a lock. You might have studied about the lock and key hypothesis. In the same manner, acetylcholine binds to the receptor. So acetylcholine is the key, receptor is the lock. So once the key binds to the lock, this lock opens. Once this lock is opened, what will happen is that the here you might have remembering in your physiology class, the outside of the membrane will be positively charged, inside will be negatively charged. Outside there will be higher concentration of which ion, outer which ion will be higher. Anyone? No, Abhishek. Outside extracellular fluid, sodium, sodium, it's sodium. Inside potassium is higher. So outside here sodium will be higher, so sodium is low over here. So once this lock is opened, because of this concentration gradient which is present in the outside extracellular fluid and the intracellular fluid. Concentration gradient means here sodium is concentration is high, the sodium concentration is low. So the key acetylcholine when binds to the receptor, that is the lock opens because the concentration, there is high concentration of sodium outside and sodium concentration is low inside. All the sodium ions starts moving inside. So this is what happens normally in a signal transmission in a synapses. So what will happen is that if the key remains attached to the lock, what will happen is that the lock is opened all the time, just like a door of your home which is open for 24 hours. The persons can come and go at all the time. So in the night you will close the door. Once the need is over, you will close the door. So in the same manner, once the signal is transmitted, that is, there is no further purpose of it. Once the signal is transmitted, the key has to be removed so that the lock, the door should be kept in the closed condition again. Otherwise, the door will be remained open forever if acetylcholine or the key is attached to the lock. So, in order to prevent continuous opening of the receptor, this acetylcholine has to be removed. So, this acetylcholine is removed by an enzyme called as acetylcholine esterase that you might be knowing. So what will happen is that the acetylcholine esterase will come. It will remove the acetylcholine so that the door will become closed again. So that once the signal is transmitted, the receptor closes again. So how it is removed? This acetylcholine, it is degraded by acetylcholine esterase. It is an esterase. That means it breaks ester bond. Acetylcholine is an ester. I will show you the structure of it. Just like a synthetic pyrethroid, acetylcholine is also an ester. So this is an esterase enzyme. That means it will break the ester bond and it will lead to the formation of choline and acetic acid. I will show the structure of it. So acetylcholine will be broken down by acetylcholine esterase into choline and acetate, choline or acetic acid. And this choline is again taken back into the presynaptic membrane. It reacts with acetylcholine, acetyl coenzyme A. I think you might be remembering about the Krebs cycle and all, which is happens in mitochondria, wherein acetyl-CoA is produced. It reacts with acetyl coenzyme A and it will again form acetylcholine. So this procedure continues. This is what normally happens in a normal system. So, in the earlier first, third, or fourth classes, I think I might have told you about ligand gated and voltage gated ion channels. So, which is this ion channels, this receptor? Either it is ligand gated or voltage gated. Answers, please. Yes, Shika, it is ligand gated because it is open based on ligand. That is, the ligand is acetylcholine. The key is the acetylcholine, that is the ligand. The ligand binds to the receptor, it opens. So what will happen to the, see, I will try to draw a structure over here. See, I am drawing, this is the tip of the axon. From here, we will be, the signal has to be continued over here. So this is a ligand-gated receptor. Here is where the neurotransmitter acetylcholine has been released, and once it is released, it binds with the ligand-gated acetylcholine receptor, and this receptor opens. But this signal has to be transmitted through the entire length of the neuron. Here, only here, there is a change, there is a slight change, and there will be a change in the voltage because of the release, because of the influx of sodium ions. So what will happen, what could be, should be done to perpetuate the signal towards the entire neuron? Take the example. We had a signal, say, we touched a hot object. We touched with the end of the finger. And this signal has to be transmitted to the central nervous system. So, for each axon, at the tip of the each axon, we have a synapse, and from the synapse, the acetylcholine is released. It transmits the signal, but from there, it has to be transmitted along the entire length of the axon. There is no acetylcholine over here. Acetylcholine is released only into the synaptic cluster, but here there is no acetylcholine. So what will happen is that here we have certain ion channels. I will draw it like this. Okay. These ion channels are nothing but transmembrane proteins. Transmembrane proteins means these are proteins that lies across the membrane. This is the nerve membrane, and these proteins lie across the membrane. You might have studied about the structure of a membrane, cell membrane. You might have studied about fluid mosaic model. Haven't you studied fluid mosaic model? Yes. So what is the mosaic pattern in that? In the fluid, what constitutes the mosaics in that fluid mosaic model? So what will be lying in between this? You might have studied that. Proteins, yes, yes. So here, these are this just like fluid mosaic model. This is the membrane. It contains of transmembrane protein that runs across. It is called transmembrane because this protein. See, I will draw the membrane. Okay, this is called transmembrane because it runs across the membrane. Okay, this is ligand gated. I will draw one more thing. Plus. Here it was plus. So here you can see that here this is the basic condition. Acetylcholine is released. Acetylcholine binds to the receptor, and before binding, here the membrane potential is positive. Here it is charge is positive. Outside it is positive. Inside it is negative. Once the acetylcholine binds to the receptor, it opens the receptor, and what will happen is that all the sodium ions move inside. Once the sodium ions move inside, what will happen is that the outside becomes negative and the inside becomes positive. So because of the binding of the neurotransmitter acetylcholine, the receptor opens, the ligand gated receptor opens, the sodium ions move inside, and inside become positive and outside become negative. Here, this membrane is continuing. Here, we have a ion channel which is voltage gated. That means here the gate opens or closes based on the voltage which is neighboring to it. It senses the voltage near to it and it responds, it opens or closes based on the voltage near to it. So what happens is that once the uh, neighboring if once it here earlier it was positive, now it is converted because of the binding of acetylcholine, outside become negative, inside become positive. This change in potential is sensed by this voltage. Here it is a ligand gated ion channel. This is a voltage gated ion channel. If acetylcholine binds to this voltage gated ion channel, nothing will happen because it can't bind to a voltage gated ion channel. But if there is a slight change in potential near to this voltage gated ion channel, this voltage gated ion channel senses that yes, there is a slight change over here, and this voltage gated ion channel opens. And because of that opening, again, what will happen is, okay, I will draw a few more. So this voltage gated ion channel senses that yes, there has been a change in the potential near to me. I have to open it, so it opens. Once it opens, what will happen is that inside becomes positive and outside become negative. So here that change happened. Immediately, this is another voltage gated ion channel. It also senses that yes, near to me, there is a change in potential and I will open myself and it opens, and again the voltage gate it opens and there will be a change in the potential and inside become positive and outside becomes negative. In this manner, there is the entire nerve membrane consists of voltage gated ion channels. So because of this, as the voltage nerve membrane is lined with innumerable number of voltage gated ion channels, so proteins, this change in the potential which initiated in the acetylcholine receptor is transmitted across the nervous system. Do you understood how a nerve impulse is transmitted? Yes or no? Or do I have to repeat it again? No answer? Yes. Yes. Abhishek, because Sri Lakshmi. Sri Lakshmi, did you understood? Ketilla. Okay, I will. Oh, Srisha, you did. Okay, I will just repeat it. Repeat it once more so that it will be clear to you. Okay. Here, what happens is that we have two types of ion channels. One is ligand gated and another one is uh, voltage gated. This ligand gated ion channels are located in the postsynaptic membrane. So here in the postsynaptic membrane, the ligand is acetylcholine. The acetylcholine binds to the receptor. This ion channel opens. Earlier it was positive because outside it was sodium channel, sodium ions was higher. It opens. All the sodium ions move inside. Because of the movement of sodium ions inside become positives and outside become negative. This is what happens when a ligand or an acetylcholine binds to a receptor that you might have studied in the class. So here there is a change in the potential in the postsynaptic membrane. But how this potential is transmitted all along across the nerve? Here comes the role of voltage gated ion channels. The entire nerve membrane is lined with voltage gated ion channels. In synapses, it is ligand gated, but in the nerve membrane, the rest of the nerve membrane, we have voltage gated ion channels. So, this voltage gated ion channels, what will happen? What it will do is it senses the change in the potential near to it. So the voltage gated ion channel, which is closest to the ligand gated ion channel, it senses once the acetylcholine binds, when sodium ions move inside and there is a change in potential, immediately this voltage gated ion channel senses that yes, near to me there is a change in the potential. So it senses the change in potential, the voltage gated ion channels opens and all the sodium ions move inside, and because of that inside become again positive, and the next voltage gated ion channel which is lying next to it senses that yes, there is a change in potential near to me. It starts opening again, sodium ions move inside. So this is the way nerve signal is transmitted across the nerve membrane. So Suresha, did you hear it now? Yes, okay, fine. So this is how the normal thing happens. We have a ligand gated ion channel, we have a voltage gated ion channel. So what it will happen is that this is what normally happen, and acetylcholine is the neurotransmitter release. This is what I told you till now. Acetylcholine binds with specific receptors in the postsynaptic membrane, and it changes the permeability. It leads to the inward movement of sodium ions, and it initiates the transmission of nerve impulse or the signal. So, as I told you, in order to stop the signal, as we close the door of our home, if you want to close, once you opened it, you will close it again. The binding of the use of the key, that is acetylcholine, open the door, but you have to close it. Then the key has to be removed. The key will be removed by the acetylcholine esterase enzyme. Acetylcholine is an ester, so it will be broken down into acetic acid and choline. Choline will be resorbed into the presynaptic membrane to again form acetylcholine. So this is the structure. See, you can see CH3COO, COO. This is the ester bond. CH2, CH2N, CH3. This is acetylcholine. This acetylcholine, there is a mistake over here. It should have been an arrow over here. Here it will be this is acetylcholine esterase enzyme. It breaks it down into acetic acid. CH3COH is acetic acid that you may know, and this one is choline. OH, CH2, CH2, and CH3. So this is what normally happens in a this is what normally happens in a nervous system. But what is the chemical reaction that is happening between acetylcholine esterase and the acetylcholine? This is acetylcholine. You remember the CH3COO, CH2CH2, and CH3. And this is the acetylcholinesterase enzyme. This enzyme has two sites, anionic site and esteratic site. This anionic site consists of carboxyl group. Carboxyl group is derived from aspartic acid or glutamic acid, the amino acid. The amino acid of aspartic acid, it is called as aspartic acid or glutamic acid because it is having COH functional group, the acid functional group. So here we have the anionic site. The esteratic site. Esteratic site consists of hydroxyl group. It is derived from the amino acid serine. So here CH3CO binds to this OH. This hydrogen moves to this acetyl group, and the acetic acid is removed. And I will show the next thing. And from this choline is removed, and this acetyl group will remain attached to the acetylcholine esterase enzyme. So first, what will happen? The acetylcholine will react to the acetylcholine esterase enzyme. It has two sites, anionic site and esteratic site, and it will bind to it. So this is the binding step. In the next step, the choline is removed, the esterase bond is broken, and the choline is removed, and the acetyl part remains attached to the acetylcholine esterase enzyme. And this enzyme, which consists of the acetyl group, is called as acetylated enzyme, or this step is called as acetylation of acetylcholinesterase. So the first step, there will be binding of acetylcholinesterase and the acetylcholine. We have the anionic site and the esteratic site. And in the second the ester bond is broken by the enzyme. The choline is removed, and the acetyl group will be attached to the esteratic site, and this is called as the acetylation of enzyme or the acetylated enzyme. And in the third step, again this acetyl group will be removed by hydrolysis. This is what normally happens. The steps in the reaction between, this is the normal thing that happens. Acetylcholinesterase binds to acetylcholine, there will be acetylation of the enzyme, then deacetylation. This is what normally happens. Just a minute. Okay. Then what happens when organophosphates and carbamates binds to it? Okay. This is the acetylcholinesterase. This is the esteratic site. This is the anionic site. So this is the general structure of organophosphate. ROPOR. This is the general that we have seen in the last class. So in the same manner, organophosphates are also esters. Esters of phosphoric acid. This ester binds to the acetylcholinesterase. So the binding step happens. That is the same. The first step is the same in the normal process and in the OP as well as carbamate. And in the second step, this part, this OR part, just like the choline, this part is removed, and just as the acetylcholine, the acetyl part removed, acetyl part remains attached to acetylcholinesterase enzyme. The phosphoryl part, the phosphate part will remain attached to the acetylcholinesterase enzyme, and this is called as phosphorylated enzyme. Earlier it was normally in the normal situation, once the acetyl group is attached to acetylcholinesterase enzyme, that is called as acetylated enzyme. Here the phosphoryl group is remaining attached to the acetylcholinesterase enzyme, and this is called as the phosphorylated enzyme. Okay, up to this you think it is perfect, it is almost similar to what happens, but here comes the difference in the third step. In the third step, we is told about deacetylation, that is removal of acetyl group and the regeneration of acetylcholinesterase enzyme. Here also the dephosphorylation or the removal of phosphate group can happen, but this dephosphorylation step usually takes after several hours or after several days together. That means the enzymes remains phosphorylated for several hours or several days together. That means this acetylcholinesterase will not be available to remove the acetylcholine from the receptor site. So I will show the picture again here. So what will happen is that here we are introducing an organophosphate. This organophosphate binds to the acetylcholinesterase enzyme. The phosphoryl group will remain attached to it. So the acetylcholinesterase enzyme is not available. It becomes the phosphorylated enzyme. It remains the phosphorylated stage for hours together or days together. So what will happen is that acetylcholine is there. It is attached to the receptor, and there is no acetylcholinesterase enzyme to break the acetylcholine and remove the acetylcholine from this receptor. So what will happen is that will remain attached to the receptor. The door of the receptor will be continuously open. All the positive ions will be moving into the inside of the system, and there will be continuous excitation. As long as the door is open, all the positive ions sodium ions start moving in. That means the nervous system will be continuously in the excited stage. That means repeated excitation occurs. So the only difference is that if you see the step in the reaction, EH is acetylcholine, that is the enzyme. PX is OP, that is the binding, that is the first step. And in the second step, the like choline is removed, the side chain is removed from the OP insecticide, and EP, that is the phosphorylated enzyme. And this phosphorylated enzyme has to be hydrolyzed to release the enzyme and the phosphoric acid. But what happens is that this step will not happen, or even if it happens at an extremely slow pace, and the enzyme will remain phosphorylated for a long time. So this is what happens with organophosphates and carbamates. The It reacts with acetylcholinesterase, the binding is there, and the second step will be phosphorylation. If it is carbamates that is binding to the acetylcholinesterase, that step is called as carbamylation. I'll repeat, it is carbamylation. The normal process, it is acetylation. If it is OP, it is phosphorylation. If it is carbamate, it is carbamylation. And in the third step, normally it should have been deacetylation. That means removal of acetyl group. And if it is OP, it is dephosphorylation. That means removal of phosphoryl group. If it is carbamate, it is removal of carbamyl group. That is decarbamylation. But the catch is that the dephosphorylation is extremely slow and it is an irreversible inhibition. That means acetylcholinesterase will not be available, and it leads to continuous neuroexcitation. And during the OP insecticide, we have discussed about a few pro-insecticide, malathion and parathion. So which one is the conversion product of malathion and parathion? Once malathion and parathion enters into a biological system, it will get converted to maloxone or paraoxone. Which one is more toxic, malathion or maloxone? Maloxone, yes, good. So here I told it is highly toxic. How it becomes toxic? What is the reason behind higher toxicity of malathion or parathion to compared to maloxone or paraoxone compared to malathion or parathion? See, this is the basic structure. If it is O here, that is paraoxone or maloxone, this binding is more strong. If it is sulfur over here, that is malathion or parathion, then this binding is less strong. That is why maloxone or paraoxone is more strong, because P double bond O, binding of P double bond O to the extrinsic site is more stronger compared to the P double bond S bond. So that is how malathion or paraoxone is more toxic compared to parathion or paraoxone, because P double bond O is more strongly attached to the estratic site. So when coming to carbamate, the mode of action is similar. Only thing is that the third step, that is the decarbamylation, that is removal of the carbamyl group, is bit faster. It doesn't take hours together, it takes minutes together. In deacetylation happens in seconds, microseconds. But decarbamylation, it remains inhibited for several minutes, not hours together. So hence we call the inhibition of acetylcholinesterase by carbamates as reversible inhibitor, because it can be reversed, but it takes some time. So this is the first step, that is binding. Second step, there is carbamylation, and in the third step, that is decarbamylation. The only difference is that between carbamates and OP is that the dephosphorylation takes hours. In carbamates, the decarbamylation takes minutes. But even then, it inhibits acetylcholine esterase. So this is with respect to this thing, and we have studied about the antidotes. You might have studied in UG about the antidotes for pesticide poisoning. For OP and carbamates, we usually recommend atropine as the antidote. What is an antidote? What is an antidote? Which neutralizes toxicity. Okay, which produces it. That means the thing which is used to treat any poisoning. So that is the thing. Just as a medicine, if someone has consumed, accidentally consumed OP insecticide, which medicine should be given? That is the antidote. So the antidote is atropine and 2-PAM. 2-PAM is 2-pralidoxin methiodide. Pyridine 2-aldoxin methiodide. We call it as pralidoxin. Another name is pyridoxine. Normally it is represented 2-PAM. Atropine is an antidote for both OP and carbamate. The mode of action of atropine is that I will show how it happens. So once you are administering atropine to the system, what will happen is that atropine competes with acetylcholine. Atropine has the ability to bind to this receptor, but it can bind to the receptor, but it cannot open this receptor. Just like a key. Remember, if Abhishek and Rahul are having both Hero Honda bikes, so what will happen is that both the key can be inserted into a single bike, but starting the bike requires that particular key. Abhishek and Rahul is having the same model of bike. They are coming with the key. They will try to start it. The key may be inserting into the keyhole, but we may not be able to start the bike with the wrong key. It's the same manner. As if the true key is there, the bike will get start. But if atropine is there, that means it can be inserted into the receptor, but it doesn't open the lock. So once you are inserting atropine over here, this atropine will bind to the receptor. But once it is bound to the receptor doesn't get opened. It will remain closed, just like a wrong key which will be inserted, but it will not open the receptor. That means the receptor will remain closed, so that the transmission will be stopped, so that the acetylcholine will not be able to bound to the receptor, because the atropine will be binding over here. The person with the true key cannot open the lock, because a false key is remaining attached to the lock, and the lock will remain closed. So this is how atropine functions in a system as an antidote. But this is common for OP and carbamate. But 2-PAM is an antidote only for OP insecticide, because in this OP insecticides works at this step, that is here, this dephosphorylation or decarbamylation. That this 2PAM removes the phosphoryl or carbamyl group from the enzyme and it will release the acetylcholinesterase enzyme. So what will happen is that once the phosphorylated enzyme is there, it remains there for hours together. So once PAM is injected, it can remove the phosphoryl group. What will happen if carbamylation is occurring? It will remain attached to for say 3 to 4 minutes and it will be decarboxylated. So by the time 2-PAM is injected, the carbamylation must have been completed and decarbamylation step must have happened. So there won't be any effect. There won't be any bond or the carbamylated enzyme to which 2-PAM can act. I will repeat it again. This phosphorylated enzyme will remain in the phosphorylated state for hours together. So if you take a person who accidentally consumed OP insecticide, at that stage within an hour or so, the entire enzyme will be phosphorylated enzyme. If we inject 2-PAM into that system, the 2-PAM will remove the phosphoryl group and the enzyme will be released back. So what will happen to carbamylation? It will be decarbamylated within minutes. So one person has consumed carbaryl. We are taken into hospital. By the time we reach, it took around 15 to 20 minutes. And by that time, the decarbamylation step must have occurred. So if you administer 2-PAM, it won't give any result because there won't be any carbamylated enzyme for the 2-PAM to act. So, do you know why? Do you know why 2-PAM is effective only to OP insecticide? Did you understood? Yes. Okay. Okay. Fine. And coming to the next, there is a concept called as aging in organophosphate. This is not there in carbamide insecticide. Aging is there only in phosphor organophosphates. Just 1 minute. സാറേ ഞാനൊരു ക്ലാസ്സില 15 മിനിറ്റ് വിളിക്കാം. ഞാനൊരു ക്ലാസ്സില 15 മിനിറ്റ് വിളിക്കാം. In aging, what happens is that, so I told you, the phosphorylation step in OP poisoning, it takes hours together. It remains phosphorylated for a longer time. So as the time passes, this binding of the phosphoryl group to the enzyme becomes extremely strong. And even if we inject 2-PAM, the 2-PAM may not be able to dephosphorylate it. And this condition is called aging. I will repeat it again. If the acetylcholinesterase remains phosphorylated for a longer time, it becomes extremely bonded together and the 2-PAM, even if it is injected, it cannot dephosphorylate the enzyme. And this is called as aging. So even if 2-PAM has to be used as an antidote, we have to inject 2-PAM as quickly as possible. If we delay administering 2-PAM to a OP poisoned person, the 2-PAM may not be able to work because by that time aging must have happened. The phosphorylated enzyme, the phosphoryl group must have strongly bound to the enzyme. So this is called as aging. Now, have you understood how acetylcholinesterase inhibitors such as OP and carbamate function and how antidotes function? Yes or no? Yes. 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 Okay, fine. So I will move into a small section. I will take just 10-15 minutes. By that time, I will complete the mode of action of voltage sodium channel inhibitors. How that? So before moving into this, I will ask you to recollect what you have learned during your UG and all. How the nervous signal is transmitted and all. So, just a minute. Okay. So, how the signals are transmitted in a nervous system? What is the resting potential? We'll ask the first question. You might have studied all those things in the nervous system. You might have studied action potential, resting potential. No answer. What is the resting potential of a nerve membrane? Forgot? Yes, minus 70 millivolt. Minus 70 millivolt. Yes, that is minus 70 millivolt. So once there is an action potential or a signal reaches the thing, what is the step happening in a nerve membrane? You take time to type, you can answer it. You can unmute yourself and you can answer it. If someone knows that process, activation or action potential happens. So during action potential, what happens? In the resting stage, I told you sodium is outside, potassium is inside, and once the action potential occurred, the sodium ions move inside, inside become positive and outside becomes negative, and that is the action potential, that is depolarization of the membrane. So I will, okay, I will show it over here. This is minus 70, that is the resting potential. So here, uh, this is the resting stage. Outside it is positive. See, usually we represent it over here. This is the nerve. This is the extracellular fluid. This is the intracellular. Outside is positive. Inside becomes negative. Inside is negative because outside sodium ions are more. Inside potassium ions are more. So once action potential reaches the voltage gated sodium ions channels open, all the sodium ions move inside, and here comes the depolarization or the rising phase of action potential. So all the sodium ions move inside, inside becomes positive and outside becomes negative. And immediately the sodium channels closes, and the again the sodium ions will be outside, outside become positive and inside become negative, and this is the falling phase of action potential. So this is what you have learned during your UG and PG, and this is what happens actually. I will describe all the things with a single step, single slide. Here, this is one. Remember, this is one, two, three, four, five, and in between here you can see this is the graph which I have shown you earlier. This is one, that is the resting potential. Two, three, four, five, and again one. This one, two, and three is represented over here. This is one of the finest diagrams I have seen with respect to the transmission of nerve impulses. So here what will happen is that this is the sodium channel, this light violet color, this one and this one. This dark violet colored one is the potassium channel. See, this sodium channels is these I told you earlier itself. These ion channels are transmembrane proteins which runs across the membrane. So it is a bilayer. That means two layers are there. In between, these proteins are there. This is transmembrane. That means runs across the membrane. The sodium channels has got two gates. This one is the inactivation gate, and this one is the activation gate, and this one is the inactivation gate. You can see it over here. This is the activation gate, and this one is the inactivation gate. While potassium channel is having only one gate, that is activation gate. Just like persons who are extremely rich will have two gates, one for vehicles and one for pedestrians. In the same manner, consider sodium channels as a rich person. It has two gates, activation gate and an inactivation gate. And potassium channel, the poor fellow, it is having only one gate, that is the activation gate. So this is in the rusting stage. This is the extracellular fluid. Outside it is sodium. Inside it is positive. Inside it is potassium. Outside it is positive. Inside it is negative. Okay. So what will happen is that here there is, if I am correcting this diagram, I will correct it in this manner. If an action potential reaches over here, once an action, this is a voltage gated ion channel, so it has to sense a change in potential near to it. So what will happen is the conduction is from here to here, the direction. So here, if there is a change, that means inside become positive and outside become negative. That means there is an action potential is created. So imagine that here is a synaptic membrane, and here we have the acetylcholine receptor. Acetylcholine binds over here. The acetylcholine receptor opens, all the sodium ions move inside. Inside become positive and outside becomes negative. So immediately this voltage gated ion channel senses that yes, here there is a change in potential. So immediately the activation gate opens. So once the gate is opened, I told you outside the sodium ions are more, inside it is negative, inside the sodium ions are less. So there is a concentration gradient. So all the sodium ions move inside. At that time, the potassium ions will remain closed itself. Potassium ions are pretty slow to react. Sodium ions react very fast, but potassium ions react very slowly. So immediately the activation gate open, all the sodium ions move inside, while remain at the same time the potassium channels remains closed. So all the sodium ions move inside. Inside become positively charged and outside becomes negatively charged. So at that time also, these potassium channels are remaining closed. So this is the resting stage. In the second stage, sodium ions started moving in. There is a slow increase, and immediately all the sodium ions move inside, and this is the rising phase of action potential, or the depolarization occurs. And once it reaches the stage, then the inactivation gate of the sodium ions closes. This inactivation gate of the sodium channel closes, and the sodium ions cannot move further from extracellular fluid from the intracellular fluid. Now the slow guy, that is the potassium channel, wakes up. It opens the activation gate, and the potassium ions started moving outside, because the concentration of potassium is low outside and it is high inside. So across the concentration gradient, the from higher concentration to lower concentration, potassium ions started moving out. And this is the falling phase of action potential. And there is a small undershoot, even if it is reaching the minus 70. It I told you this potassium channels are slow in nature. It is a slow fellow. So what will happen is that its opening is slow, its closing is also a bit slow. So by the time the potassium channels closes, there will be a more in a efflux of more outward movement of potassium ions. That is why the graph shoots a bit below the action potential. At that time, both the activation gate and inactivation gate of the sodium ions will be closed. The potassium ions will be remain open at that time also. later on the potassium at the resting stage, the potassium channels will be closed and the inactivation gate will be open. So this is what happens normally in a signal transfer section. Are you clear how a signal is transmitted across a nerve membrane, or shall I need to repeat it again? If I need to repeat it again, you can tell. I will repeat it again once more. Okay. So this is the resting stage. In the resting stage, this is the extracellular fluid. That means outside the nerve membrane. This is inside the nerve membrane. Here, this is the plasma membrane. Across the plasma membrane, we have proteins. These proteins form ion channels. So we have sodium channels, which allows the movement of only sodium ions. We have potassium channels, which allows the movement of only potassium ions. Both sodium channels and potassium channels are voltage gated. That means it opens in response to a change in voltage. So that is what happens. So in the resting stage, the voltage is normal. Outside it is potassium, inside it is negative. Outside it is sodium, inside it is potassium. Outside it is positive, inside it is negative. And the sodium channels are having two gates, an activation gate and an inactivation gate. And the potassium channels are having only activation gates. At the resting stage, both the activation gates of sodium as well as the potassium channels are closed. So that is the resting stage. So here, what will happen is that here there is a synapse, and in the synapse, the acetylcholine is released. The acetylcholine binds to the acetylcholine receptor. The acetylcholine receptor opens, and all the sodium channels moves in. And because of the movement of sodium ions into the inside become positive and outside become negative. So this ion channel, the sodium ion channel, this sodium channel is a voltage gated ion channel. It senses that yes, there is a change in potential near to me. So immediately the activation gate of sodium channel opens. So I told you sodium ions is more outside, sodium ions is less outside. Concentration of sodium is more outside, concentration of sodium is less outside. So there is a concentration gradient across the membrane. So if there is a higher concentration outside, all the sodium ions from the higher concentration moves to the lower concentration. So this movement of the sodium ions from the higher concentration to the lower concentration leads to the change in potential, leads to the depolarization of the membrane. It is called as the rising phase of action potential. This happens immediately as soon as the sodium channel senses that there is a change in the potential near to me, it opens immediately. But potassium channels, it is a slow ion channels. Potassium channels will remain closed during this rising phase. The potassium channel reacts to the change in potential very slowly. And later on, the potassium channel slowly opens. Once the potassium channels are opened, all the potassium ions move outside, because outside potassium concentration is low, inside potassium concentration is high, and it moves across the concentration gradient. By that time, the inactivation gate of sodium channels will get closed, and this is the falling phase of action potential, wherein the potassium channels are open, the activation gates of potassium channels are open, all the potassium ions move outside, and the outside uh, slowly becomes positive. Here, see, because of the movements of potassium ions, outside become positive. The activation gate as well as the inactivation gate of sodium channels will be closed, Again, the potassium channels are slow in nature. The closing takes a bit longer time. By that time, a higher amount of sodium potassium ions will move outside. That is why there's a slight dip in action potential. It will dip below minus 70 millivolt, and again it will close by slowly. By that time, it comes to the resting potential. This is what happens normally in a nervous neural transmission. Is it clear now? Yes. What about others? Yes. 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 Rahul? Yes. Okay. So what will happen one? What are? Can you give a few insecticide group which acts on sodium channels? OC. Yes. One more group. One pyrethroids. Yes. Okay. Yes. Pyrethroids. So what will happen when an organochlorine and, or a synthetic pyrethroid comes? It binds to the receptor. Not binds to the receptor, it binds to the voltage gated sodium channel. It has this synthetic pyrethroids and organochlorines has the ability to bind to the voltage gated sodium channel. And what it will do is it keeps the voltage gated sodium channel open, and this because of this continuous opening of this voltage, that means the voltage gated sodium channels remain open all the time. That means the sodium ions will move all continuously into the intracellular fluid. So there will be a continuous change in action potential. That means the nerve impulse will be transmitted continuously across the nervous system. That means continuous excitation of nervous system occurs. So this is what I will discuss: signal transduction, resting phase minus 70 millivolt. Impulse reaches the action, sodium permeability of the membrane increases. That means sodium ions move inside, and this is depolarization. And potassium ions also contribute to depolarization, but slowly because it is a slow ion channel. And sodium channels has two gates, activation gate and inactivation gate. Potassium channels are only activation gate. It slowly in response to depolarization. In resting stage, activation gates of both ion channels are closed. Only the inactivation gate of sodium channel is open. In rising phase, the activation gate of sodium channel open, potassium channel it is closed. In the falling phase, inactivation gate of sodium channel is closed, but potassium channel is open. In the positive phase, that is here, that is both gates of sodium channels are closed, but potassium channels are open, and there is a positive after potential because of this slowness of this potassium channel. That is this undershoot part. So DDT and pyrethroid binds to the sodium channels and cause delay in opening of the sodium channel. So the axon does not recover from the resting stage. It remains in the active stage, and there will be continuous transmission of the nerve impulses. It leads to excessive neuroexcitation. So this is what happens. It should have the potential should have fallen, but because of the binding of DDT or pyrethroids, it remains in the polarized state for a longer time. And coming to the last thing, in pyrethroids we have discussed about type 1 and type 2 pyrethroids, that is alpha cyanopyrethroids and non alpha cyanopyrethroids. In a type 1 pyrethroid, it will lead to repetitive discharges. That means uh, once non-alpha cyanopyrethroid, that is permethrin and all binds, it closes, opens again, closes, opens again. That means it will be repetitive discharge of sodium ions. In type 2 pyrethroids, once it binds, it opens for a longer time and sodium ions will be moving. So it will not cause repetitive discharges. The only thing is that it remains open for a longer time and there will be a depolarization. The phase will continue for a longer time. While in type 1 pyrethroid, it closes, opens. That means there will be repetitive discharge. That means continuous excitation. Whatever it may be, type 1 or type 2, the result will be the same. There will be continuous excitation of nervous system. And another difference between type 1 and type 2 pyrethroids is that type 1 is negative temperature coefficient. That means it is more toxic when the temperature is low. In type 2 pyrethroid, it is positive temperature coefficient. That means it becomes more toxic when the temperature is high. As the temperature increases, toxicity also increases. In type 1 pyrethroid, as the temperature increases, toxicity decreases. So this is the difference between type 1 and type 2 pyrethroids. Usually I used to take these two as two separate classes. I combined because I thought I can combine it together. Are you able to understand how the insecticides work at the physiological level? Yes or no? Yes. Okay. I will ask one question. Uh, I don't expect if that is a logical question. If try to answer it, whatever the thing that comes to your mind, you can answer it. I told you. Oh, I will. Okay, here. See, there is a concentration gradient across the membrane. Outside sodium ions are more inside potassium ions are more. So there is a gate opened over here, sodium channels, and sodium ions are moving inside. A gate means anyone can move inside and outside. Why potassium ions are unable to move over here? Why there is a separate gate for potassium? Why when the sodium channels are open, why potassium ions are unable to move outside? Why it's so? There is a gate, it is opening, and there is a high concentration of potassium inside and high concentration of sodium outside, and there is a gate which is opened, and this through the open gate only sodium ions are moving inside and the potassium ions are not trying to move inside, move outside. What could be? Any? Have you thought of it? Shall I answer or will you able try to find it out? Why? No one is responding. Are you thinking? എന്തെങ്കിലും ഒന്ന് പറയടോ ചോദിക്കുന്നതിന് അറിയില്ല. Will you try to find it out? Okay, I'll try to give a simple explanation to it. Here, uh, what will happen is that this is the sodium ions and potassium ions. Um, this which one is the size of sodium ions or potassium? Which one is bigger? Yes, molecular weight. That is one thing. Yes, yes, yes. You get it. Then comes the next question. Then the potassium channels are open. Which one is bigger, sodium or potassium? Potassium. Okay, agreed. You're good in all of you are good in chemistry. As you move down the periodic table, the size becomes uh, increases. So even if the sodium channel is open, the potassium channels cannot move outside. Then what happens when the potassium channel is open? Because it is bigger in size, it permits the movement of potassium ions. And what about sodium, which is smaller than potassium ions? It can also move out. What will happen is I will answer it. That is a molecular biology aspect. Here, there is a selectivity filter over here. There is a filter. Consider there is a filter over here which allows only the movement of potassium ions. It prevents the movement of sodium ions. So the potassium channels is having a selectivity, if we call it as a selectivity filter. It is a filter which permits the movement of potassium. And how the selectivity filter works and all, I used to teach in the advanced toxicology course. So I think now you understand how the system works in an insect. Isn't it clear to you or not? Yes or no? Yes. Yes. If someone has not seen that videos uploaded in the Moodle, try to watch it again. Once you today, try to watch that again so that you will be able to understand it better. Now you have some basic idea on how this works. Now there are several videos. I have given only the uh, simpler videos in the Moodle. If you just type mode of action of sodium channels or how sodium channel functions or how acetylcholine esterase inhibitors work, there are several videos in there. Okay, Rahul, hungry?